Work reversible, no? Work reversible and isothermal van der Waals gas. This is the formula, no? And so what we do now is, because based on the given, we have P1 and P2. We have a temperature value. For the first two conditions, it is isothermal, so we only need this temperature. But if ever we need T1, if ever we need another temperature, I don't think that is possible now. Because in this formula, we need volumes 2 and 1. So how do we find them? By the way, the van der Waals equation of state is P equals nRT over V minus NB minus A n squared over V squared. I think this is the one. Let me just verify. Yep, sounds about right. So this is the van der Waals equation of state. And since we have pressures 1 and 2, we can find volumes 1 and 2 respectively. This is my thinking strategy, no? 10 atmosphere, that is 101,325 in Pascal. 10 times 101,325. We want to express it in SI, no? In SI. Okay, so N, the number of moles of our gas is 1.5 times 8.314, that is the universal gas constant, joule per mole Kelvin, since we want our work in joules, no? It says here. Temperature, that is this one, the 523.15 over V minus 1.5 times. Okay, before we proceed, we need to convert these already. One atmosphere, 101,325 Pascal, and then 1,000 meter cube square. We'll do the same for B. Here, 1,000 liter, 1 meter cube. That's it. Okay, calculate. 2.303 times 101,325 over 1 times 1 over 1,000. What we get is 0.2334. The new unit is now Pascal meters raised to 6 per mole squared. Basically cancel atmosphere as well as the liter squared. Okay. Letter B. Oh wait, by the way, we can store this as the A in your scientific calculator for later. For letter B, 0.0431 no? Times 1 over 1,000. Okay. We'll start this as B. Okay. So now the B is here minus A and then 1.5 raised to 2 over V squared. We're going to shift solve, no? 10 times 101,325 equal to 1.5 times 8.314 times 523.15 over x minus 1.5 times the stored value B minus stored value A times 1.5 squared over x squared. Don't forget the squared. Shift solve. What's gonna be the answer? This is V1. And then after this, we're gonna find V2. For V1, it's 6.423 7 times 10 raised to negative 3. I'll start this as C. For V2, honestly, it's the same thing. So 101325 is our P2, no? This one. So everything else is the same. I'll recalculate. 101325 equal to 1.5, 8.314, 5 to 3.15 over x minus 1.5 times b minus a times 1.5 squared over v squared. So the answer here is 0.06 something something. There. We'll store this as D for convenience. Store as D. Okay. Okay, so after that we now have V1 and V2. We can go back to this whole formula. Substitute now, no? Negative 1.5 times 8.314 times the temperature 523.15 times ln. V2 is what? D minus 1.5 times B over C, no? C is ours. We start V1 as C. And then minus 1.5 times B minus A times 1.5 squared times quantity 1 over V2. V2 is D. And then 1 over C. Is everything in SI unit? This one is in Kelvin. This one is in joules per mole Kelvin. This one is in mole. C and D are in meter cube. No? That's supposed to be in meter cube. And then, how about B and A? We already converted them into SI units, so everything is in SI. We can now plot this in the calculator. Negative 1.5 times 8.314 times 5 to 3.15 times ln. The reason why we are storing values is to reduce the risk of mistyping, no? It simplifies the work, basically, if we do this. So it's possible that we are able to show the process correctly, but because the numbers are wrong in the way they are inputted, you don't get full points. Your review is in a way sayang lang, no? Because even if you got it right, then even if you get the method right, if you don't get the right answer, it's not going to give you as much points, no? So the resulting answer is 15,022. I think I remember having this answer in the exam, fortunately. Even though I just realized now that we can resort to storing values. It reduces the risk. It's less stressful, no? Low cortisol. So that is it for letter B, for reversible and isothermal, assuming that the methane gas is a van der Waals gas, a kind of real gas. How about the third condition? This is reversible and adiabatic. What does it mean if the process is adiabatic? This basically means heat transfer is 0, Q is 0. And in this condition, we assume that the gas is ideal. So there is a formula for this. Reversible and adiabatic. The work reversible for adiabatic process is P2V2 minus P1V1 over gamma minus 1, such that the gamma is the adiabatic index. How do we get that? In this condition, we are told that the gas is ideal, right? Methane, CH4, is ideal gas. So let's bring out Cp and Cv. For Cv, this is 3R. Cp is 4R. gamma is equal to Cp over Cv. Cp is 4R, Cv is 3R. That's 4 over 3. So that's how we got the gamma. Pressure 2, we do have, no? Pressure 2 is 1 atmosphere. Let's convert it to Pascal. 101,325 Pascal. And then volume 2. What is our volume 2? It's in meter cube, no? Let's write it as B, no? Sorry, D. Stored value D. Minus P1. P1 is 10 atmosphere. 10 times 101,325 Pascal times V1, which is C, divided by gamma, which is 4 over 3, then minus 1. Okay, calculate. What does the calculator say? 101,325 times D minus 10 times 101,325 times C over 4 over 3 minus 1. Interesting. 41.43 joules. I remember getting 167 here. I think this is probably where I got it wrong already. Dang it. Anyways. For the fourth condition, adiabatic against a constant external pressure. P external equal to constant equal to 0.5 atmosphere, assuming that the gas is ideal. Okay, so for the work in this scenario, this is, since P external is constant, this is case 1 of moving boundary work. So that's gonna be negative P external, and then V1, V2, dV. Yep, sounds about right. And then negative 0.5, just substitute. Oh yeah, this is also the part where we use the volumes, no? The volumes that we found, V1 is... Oh, okay. So, we're gonna make some tweaks. What I mean by that is, our V1 is in meter cube, no? C, meter cube. We want to convert it into liter. 1,000 liter is to 1 meter cube. So, that's gonna be 1,000 C liters, no? And then here, D meter cube. We do the same thing, basically. So that's gonna be 1,000 D liters. We'll use them here. What's our lower? What's our V1? V1 is 1,000 C. And here it's what is it again? 1,000 D. So notice we can rewrite this as negative 0.5 atmosphere. Integral rather is V2 minus V1. So in other words, 1,000 D minus 1,000 C. These are all expressed in liter. So that's basically, the unit is basically liter atmosphere. Remember, in the instructions, we are told to convert, our work is supposed to be in joules. So here we convert 0.08 to 0.6 liter atmosphere. And then here, 8.314 joules. That is our conversion factor. No? So, negative 0.5 integral, and then from 1,000 C to 1,000 D. And then multiply with the conversion factor, 8.314 over 0.08 to 0.6. Our answer is negative 2,936 joules. My answer is similar, I remember. Yeah, my answer is pretty similar. It's just letter C that's pretty messed up for me in this part. Let's move on. Uh, let's answer another question. So we have to calculate the work done by a sample of 1.25 moles of argon gas that expands from, okay, so P1 is 0.2 liters, P2 is equal to 1 liter at a temperature of 25 degrees Celsius against a variable external pressure. So P external is a function of, in this case, V, volume. Varies according to volume given by expression PV raised to n equals K. So this is a polytropic process because of this, because this is a polytropic index. P external in this case is equal to KV raised to negative n. That's the template, no, in a way. In the calculator, this is y equal to ax raised to b. In other words, in the Canon 789 SGA calculator, this is power, PWR. When you press menu, you go to mode 3 stat, no? For if you want to plot values and look for AB and the regression. So we are given data, no? In this case, I'll just write it down. P, pressure in atmosphere, we have 0.8501, 0.5111, sorry, for decimal places, 0.3315, 0.2411, 0.1885. And then volume in liter is 1, 2, 1.5, 2, 2.5, and then 3. Okay, so it's already been established here that, here rather, that y is to the P external, in other words, the pressure, and our x is what? The volume, no? So how do we arrange this table? This is the volume, this is the pressure, this is x, this is y. Plot them in the calculator, go to menu setup, to stat, and then look for this one, the y equal to ax raised to b. And then input these values. 1, 1.5, 2, 2.5, 3. 0.8501, 0.5111, 0.3315, 0.2411, 0.1885. Okay. And then look for A. A is 0.8667. B equals negative 1.3039. Okay, so that's it. Finding regression is optional. It's not really so useful in our scenario right now. A corresponds to what? The K, no? K. And then B to the negative n. So this is our negative n, this is our K. Let's now bring it back to the original equation. P external. Wait. So this is, we're still tasked to look for work, no? In this scenario. So work equals negative, then integral P external. Oh wait, this is case 2.3. Yeah, polytropic process. Case 3 is free expansion. Basically, the work there is always going to be 0 because P external is 0. Okay, volume 1, volume 2. Sorry. This is volume 1, this is volume 2. I got confused. Anyways, P external is this one, no? K 0.8667 integral V raised to negative 1.39 dV. From V1 is 0.2 liter. V2 is in 1 liter. Is 1 liter rather. Okay, so that's it. This is, expect the answer to be in atmosphere liter, no? Liter atmosphere. So we apply a conversion factor again. So apparently this is the answer. What if we did not apply the conversion factor? What would our answer be? 1.94. I don't think I had an answer like that. It's somewhere around the hundreds when I took the exam. I hope it's a good sign. I mean, I spent so much time reviewing for this. It's technically a preparation for actual thermodynamics. Because right now these are just the basics. Physical principles. Anyways, let's go to the next problem. So 2 moles of H2 gas initially, so T1 equals 25 degrees Celsius, assumed an ideal gas. No? So it absorbs 2000 joules of heat in a constant pressure vessel. So what is constant pressure? This is isobaric. No? What we are asked to do is to calculate T2 in degrees Celsius, the final temperature, and the change in internal energy of the H2 gas. So 2 missing items, no? For isobaric, let me just detail some formulas. Q, and then work, and then enthalpy. Enthalpy is always going to be NCP dt in the case of the 4 main polytropic processes, except for, among the 4, it applies to 3. What's not part is the isothermal process. Because in isothermal, dt is 0 because temperature is constant. No? The more you know. So here, okay, we'll leave it at that. Work is negative P external dV V1 V2. In an isobaric process, it happens that Q and delta H are the same. Why? Let's see later. NCV dt T1 T2. Let's bring out the first law equation. Delta U equals Q plus W. Let's just keep this as is. I can't really recall right now. I'm not looking at my notes regarding how they are the same, what made them the same. But there's a derivation for that, or an explanation, at least. 2000 joules is to Q, no? And it happens to be delta H as well. So apparently they have the same formula, Q and delta H, for isobaric process, NCP dt, no? So 2000 equals N, so 2 moles, and then Cp. Oh yeah, in this problem, Cp molar is detailed, no? 27.28 plus 3.26 times 10 to the negative 3 T plus 0.5. This is in SI units, no? Temperature in Kelvin, Cp molar in joules per mole Kelvin. Same unit as the 8.314, no? Universal gas constant. Okay, so that's Cp, no? Cp and then dt, T1, T2. What we're looking for is T2. T1 to 25 degrees Celsius is 298.15 Kelvin. Let's convert it to Kelvin already. The thing is, here, what I did in the exam was, we already know Cp. It's modeled by this one. However, technically, since we assume that H2 gas is ideal, H2 is diatomic, no? So ideal diatomic gas, its CV is equal to ideal diatomic 5 over 2R, and its Cp is 7 over 2R. I used this one. Here. Let me show you. So 7 over 2R is the Cp. And then this one and this one would be rewritten as T2 minus T1. And then equate to 2000. So this R is the 8.314. Okay? So everything is in SI units. The T1 is what? 298.15 Kelvin. Solve for T2. So T2 is 332.52 Kelvin. We are being required to have it in degrees Celsius. So minus 273.15, that is 59.37 degrees Celsius. So that's the first answer, my first answer. It's unverified, but from my explanation naman, right, it's pretty logical. This is from a complete table. We can use those values for as long as it is acceptable to assume a gas to be ideal. No? In this case, the instruction stated that we can assume that H2 gas is ideal. No? So we made use of that premise. So, okay. Now, we search for internal energy. But wait, let's verify. Let me verify something. Sorry. I repeated it twice. That's 0.5 times 10 to the fifth. No? Lower limit is 298.15. Upper limit is 332.52. Okay. So it's pretty approximate naman. So how did I check if this temperature is okay? This is what I did. So go back here. Let's assume that the Q is missing, no? We don't know. Let's pretend that we don't know that it's 2000. And since we have T2, we put it here. 332.52. And then temperature 1 is 298.15. And then our Cp is this entire thing. And then we put dt at the end. So the calculator said that it's 1981 joules. It's not exactly 2000, but it's an approximation. So I don't know if that's gonna be acceptable. That's the thing. Because I think there's another way, a more accurate way of solving this problem. It's actually, let's try to do it now. Let's set aside internal energy. This is just for experimentation. I haven't actually proven that this method works, but in theory it should. Um, CP. The problem is, this is actually what we want. So 298.15 Kelvin is here. We have 2000 joules at the other side. And then we have CP here. No? And then DT. Ideally, we can just simply input this in the cycle and it would solve for T2, but that's not the case. So that makes the solution much longer, no? In the sense that this is what it looks like. So this is T2, T2 minus, so repeat, such that this one is, you replace T with 298.15. No, that's it. So that's basically T2 minus T1. No? How do we do this now? I think this we can store as E. No? Let's store it as E. 27.28 plus 3.26 times 10 to the negative 3 times 298.15. Am I typing it correctly so far? 27.28 plus 0.5 times 10 to the 5th over 298.15 squared. Store as E. Okay. And then, so that's gonna be 2000 equals to times this minus E. So we basically shortened, no, the equation so that the calculator could compute faster, no? Especially for our case, the professor doesn't allow the use of calculators that are fast, no? And those fast calculators are usually the ones that are not allowed by the PRC. In the Philippines, that is basically the commission that regulates, I don't want to be technical. It basically, in engineering board exams, you're limited to the use of just a few calculators, allowable ones, non-programmables, and they're usually slow, like the 789 SGA Canon. Okay, I am done inputting. I think we can shift solve now, no? This is crazy. Oh wait. It's a really big number. I don't know why. I don't know what's wrong. 2000 equals 2 times quantity 27.28 plus 3.26 times 10 to the negative 3 x plus 0.5 times 10 to the 5th over x squared minus E. I don't see anything wrong. Yeah, temperature 2 is 307,219. I don't know why, but so yeah, actually this was my first instinct in the exam. I didn't push through because the number was just too weird, no? Uh using this one, the estimation, it was more believable, no? So, let's solve for internal energy. Internal energy is essentially the same formula for all cases also, in the same way that enthalpy is the same formula for all three for three of the four polytropic cases. The one exempted is the isothermal. Because in isothermal process, uh, dt is zero, no? But and like delta U and delta H both have dt in their formula. So they're all zero also in isothermal process. So what's the number of moles again? 2, no? 2. T1 is 298.15. T2 is T2 is what? Ah, 332.52 Kelvin times CV. Oh yeah. There's another relationship you have to know. CV, no? CV. No. CP minus CV equals R. We're looking for CV, so it's equal to CP minus R from that relationship. So how do we apply that? CP minus R. We're gonna have to move this. There you go. So just copy everything. This CP is gonna be this one. Imagine how many times I had to write this in the exam. So you had to be efficient. On iPad you can just copy paste, but in the exam you cannot. Minus 8.314. Okay, so this sounds about right. Just input everything. 2 and then 27.28. Do we need a conversion factor? Everything is in SI unit. So SI units. So I don't think we do need. Delta U is 1409 joules. That's it. What if we tried to use this one instead? 5 over 2R. So how does that change the solution? Sorry. Why is the iPad so clumsy these days? It's basically entropy. It's aging na. CV. CV is 5 over 2R this time. Yo. Oh, wait, sorry. Similar value. 1429 joules. Okay, that's basically it. That was my exam. Actually 4 questions, but I only was able to answer 3, um, imparting this kind of logic no, in the exam. Because the first problem was derivation. We were instructed to evaluate the difference between isobaric heat capacity and isochoric heat capacity. Basically, Cp minus Cv at standard temperature pressure for CH4 gas assumed as VDW gas. I had no idea how to derive. So that's already 70, no, not 70, 30 points out of 100 that you won't be able to get. That's it. Yeah, that's basically it for this video. Bye-bye.